And there are two final topics I wanted to discuss. The first of them is hybrid modeling. And this discussion of hybrid modeling will not be a spectator sport. It will involve opening some successive models from the library of example models. And I would suggest that you prepare yourself to access said models so that we can quickly go download them. And I want to particularly highlight the area of that AnyLogic 8 examples, which is entitled hybrid models, which provide, somewhere between 1 and 2 dozen, I think, different hybrid models. Okay. So we're going to go here and because there's an opportunity cost for each minute I spend on this, I'm not going to be able to spend a minute on discussing other topic. I'm going to go quite light on this. You'll find videos of me delivering similar material at a more leisurely pace online. But I do want to bring an experiential component into this. So hopefully this will confer some added value besides watching videos on its own terms. Okay, so pardon me. Just going to share my screen here. Okay, so I'm speaking here as well from tremendous amounts of lived experience and from the heart in terms of our experience with different hybrid traditions. And it's from a long-time conviction that system science methods are highly complementary, that they seek to answer different questions, that they have different areas of comparative advantage and specialization and areas of expressiveness and richness and power and general benefit. But it's more with the conviction as well that significant synergies can be secured between them so that we can get genuinely a whole greater than the sum of the parts. And rather than thinking about it as a matter of choosing one tradition, one horse to ride, it's a matter of, in my view, artfully mixing different approaches for different areas in a modeling project, and often in a single model for given AnyLogic's hybrid support to which they're best suited. Now, there's many advantages for this, and again, you'll find me holding forth on this. There's comparative advantage, to which I've just alluded. Different questions or different levels of analysis are needed across different areas of a system. There's different types of needs for different spheres of a system. Some may be involving resource utilization and structured workflows and service delivery, to which DES is a great advantage. Some involving networks and spatial location and individual history, to which ABM is a wonderful tool, agent-agent interactions, agent-environment interactions. And yet others which really benefit from stock and flow depiction, perhaps for characterizing theory-based understanding of evolution within a given agent, or at an aggregate level, certain types of evolution, or perhaps representing most of the population in a stock and flow way and having just parts of it represented using agent-based and discrete event simulation engaged in service seeking. So there may be, in the same model, different regions that are really well suited to these. And that's really important because I've long emphasized, and I've emphasized as a central feature of this boot camp, the fact that modeling is learning. Good modeling projects put a premium on learning from that modeling. Modeling models here are first and foremost learning tools, in my conviction. And as we learn in our modeling, often we find that our needs for level of detail, level of resolution, the types of factors, the types of drivers we wish to characterize are different than we had previously thought. Our sense of our needs, and of the right building blocks for those needs, and the foremost questions that need to be addressed evolve. And it is natural to weave a given model out of different methodologies, whereas certain needs come to the fore or retreat, you can shift the level and the type of description that you have accordingly, so that you adapt the areas of the model that make use of one methodology versus another. Perhaps you make parts that were previously aggregate with stock and flow modeling more articulated with agent-based modeling. Or perhaps you decide that certain types of characterization with networks no longer have such a primacy for your model. The focus on contact tracing is no longer on stakeholders' minds, and that would be better. The model focus will be better shifted elsewhere, and perhaps even wish to put things back in an aggregate form for that area of the model. Or perhaps you wish to nimbly examine effects of heterogeneity and collapse it up. And in which case an agent-based model will be a key tool for doing that nimbly, for doing that in an agile way. But maybe once it's stabilized, you could make use of an aggregate level model. I've spoken about stakeholder resonance. The impact on computational efficiency is very material, and the benefits and draws and needs sometimes for characterizing multi-scale modeling. ABMs have a particular role to play here by providing support for multi-scale hybrid modeling, providing the ability to articulate environments within the same model, which may be characterized with different traditions. And they offer a very natural interface with both discrete event modeling and with system dynamics. Although I will say with system dynamics, the support in any logic in terms of performance leaves considerable amounts of things to be desired. It's improved from its initial release, but it's still has some real issues with efficiency. So I'm going to be talking here from a massive amount now of lived experience, where most of our modeling projects at scale, most of our empirically grounded modeling projects are hybrid models. Hybrid models that make use of one or more of the following forms of patterns. And I've named each of these here, but we're going to go through each. So I'm not going to dwell on this particular slide, but you can always come back to this and find a high-level reference. So I'd like you to load in for each of these some models. And I want to emphasize that in each case, this is not, and I emphatically want to stress, this is not a matter of, look what we can do. This is a matter of, this is how you get extra insight. This is how you bring to the table a much greater understanding. This is how you bring together the flexibility to drive real understanding by stakeholders or real policy relevance with these models. The time for experimenting with as curiosities was decades ago, and when I was doing that. now it's about delivering value for health services inside inside a population level, with much of this types of delivery having occurred with in very applied health service delivery or public health contexts in practicing organizations. So I'd like you to load up a model provided to you in that set of example models called multi-clinic SIS hybrid saturation effects and lock-in. It's in the hybrid folder of that AnyLogic 8 examples. Okay. And maybe just to show that, it's in AnyLogic 8 examples, right? And then you go to hybrid models, and then you go to this okay, here we go. Multi-clinic SIS hybrid saturation effects. Now, this model is worth examining, and if I had my druthers, if we had an extra hour, a possible good use of that time would be to spend half an hour just on this model, because I actually think there's a lot of principles to learn from system science from this model. Principles of lock-in, principles associated with path dependence, principles associated with tipping points. This model illustrates them well, but in our case, we're going to have to cut to the chase as far as the hybrid modeling components. So what I'm going to do is I'm going to close other models. Boom. And I just want to highlight that this is a model whose structure depicts a population, set of homes, and a set of clinics. Pretty familiar stuff. A population size and a count of homes, and a set of other parameters in a manner of use with which you will be well acquainted. If we were to go to the clinic now, what we would see is a departure from our experience. What you see is a discrete event simulation workflow where we have a pool of healthcare workers where people come in, they're awaiting care. If they don't secure care within 300 minutes here, then they will leave without being seen. And that's this path here where they will depart said facility. Otherwise, they will, after finishing waiting, undergo treatment. The treatment will either be successful or failure. If successful, they will be sent an appropriately blunt cured message. And by virtue of being sent this message by the curing hand of the physician, they will go back and they will complete care. They will, excuse me, it's not that one at all. It's, yes, this infective and symptomatic. They will go back to a susceptible state. So they are afflicted by so individuals can be infected by a condition in the classic way. They go through stages, but what's notable is that the infectious stage is recovery from it is treatment mediated. So they need the healing hand of the physician, so to speak, in order to help them recover. And it's when they receive that cured message in this workflow, and only when they receive that successfully, that they go on and recover. You'll notice here this is probabilistic. This is a bit like so this is a chance node or chance outcome node, and it's only if it's been successful, they're sent the cured message. If there's a treatment failure, they're not cured. But following that, they don't know whether they're cured or not, and they free up any resources and depart said facility, which sends them at a person level home. So an individual here is generally in a state of not seeking care, but once they become exposed and they are ill, they can, and once they reach a point where they're infective and symptomatic, they are eligible at a certain hazard rate per day of finding the nearest clinic and presenting to it for care. Okay. And once they reach that clinic, they arrive there, you'll recognize this arrival transition. They enter the clinic and put themselves in line to secure care. So they presented at the clinic at this very entry point, and they come in and they enter in line. And the key nexus there that I want to emphasize is indeed that place where they put themselves in line. So I want to highlight this model characterizes individual level natural history of infection, individual care-seeking behavior contingent on that natural history of infection, their state in the natural history of infection. But the way it's designed, they seek out a clinic, they transit to the clinic in a way that will be familiar with everyone who's been here the past few days. And having done so, they put themselves in line, and then the logic of the clinic takes over. Now, when they finish and they depart the clinic, they will receive this message saying, you've departed clinic, and they'll now no longer be in a seeking care state. And of course, there's logic here involving infection transmission that I won't get into, but it's pretty familiar to what you've seen. Now, if I had my druthers, I would show you the characteristic properties of complex systems in terms of path dependence, lock-in, tipping points, and so on. And you can see comments on these here. Though I know I might require 6 clinics. But I do want to show this running to further emphasize the dynamics induced by said model. You'll notice some number of individuals start yellow, indicating their infection status. And by all accounts, we should have colored these in a manner fitting to their appropriate state here. So this is yellow indeed, and this is red, and I should, for the new model version, I should mark that as such. But we'll speed this up here. Here we go. Okay, so those individuals became ill, and you'll notice that here's the clinic, and they're presenting there for care, but they didn't present so quickly as to head off the infection spreading. Think of it as an STI like gonorrhea or chlamydia, which particularly persistent one for which they need to secure care with antibiotics. So these individuals are presenting for care, but it keeps on popping up, gopher-like, throughout the system here. And we have a number of counts of illness, but we also have in the upper corner here, we have, this is not illness count, this is the capacity utilization for the clinic, how busy that clinic is. And what we see is that the clinic is growing increasingly busy with a growing number of individuals who are seeking care. The clinic is conferring value and are conferring care and thereby curing people, which affects the public health status of the population. It means that person returns home, is no longer spreading in a state to spread infection, right? They're susceptible. But that clinic is having has had a challenging time keeping up with this spread of infection, but it's holding its own right now. But as time goes on, there's a risk that it will get to reach a tipping point. And at that point, at that said tipping point, let me get this out of the way. Okay. At that tipping point, I want to emphasize that the state changes dramatically. We have very high capacity utilization, which means that people are waiting in the clinic for very long periods of time. Most of those people are therefore leaving without being seen. The healthcare workers are at very high levels of utilization, 80% here. So most people are presenting for the clinic are not securing treatment, and they are engaged in continued infection spread as a result. The clinic is maxed out. The people who leave without being seen end up going back into the community. They can spread the infection further, causing yet more visits to the clinic and yet overloading it faster. If this sounds like a vicious cycle, it is. And you see that the system is in this new state where we have absolutely massive numbers of individuals infected at a given time. Here, this is I believe, the prevalent case count. And the clinic is absolutely maxed out. We can add clinics. I've added a second clinic here within the system to help serve people. The count of clinics is 2. And you can find a second clinic here being visited by people. If you should be able to find that if you look closely. I've just added a third clinic. You can see there's a second one here, one up here, and a third one here. And people are presenting to the nearest one, but that is not really helping. We have 3 clinics. We have 4 clinics. And yet we are still looking at a lock-in situation that's adverse. We had path dependence. It came to this very serious outcome. If only we had treated those initial few people quickly enough, we could have headed it off so much more easily. But now we're just treating massive volumes of people because we're in constant firefighting mode with 4 clinics. Here are 5 clinics. 5 clinics being required to serve the treatment volume. And even so, these clinics right now are at very high levels of capacity utilization. Distressingly high levels. I'm not even simulating staff burnout, right? 5 clinics. And yet it still rages at exceptionally high levels. If I go to 6 clinics, I can bring down the infection level, and you'll notice the capacity utilization is dropping. But the infection remains stubbornly persistent in the population. We're still somewhere around 90% of utilization. One more time, I'm now at 7 clinics. And yet again, we bring down the infection levels, and you'll notice the utilization is correspondingly dropping. Because it's dropping, we're getting faster care delivered. Because we're getting faster care delivered, we're getting individuals treated more quickly, and therefore they spread infection. We're about to crack 80% utilization on a downwards trajectory. The infection is knocking around still, but now we're below 80%, and it's saying still above 500 people infected out of 1,200. One more clinic to serve the very high load. 8 clinics. If only we had treated those first few people well. Check it out. And again, each clinic is serving massive volumes. But you'll notice most people seem to be, and that statistic on load is still catching up to the realities of what's going on. It's kind of an average utilization. So we're seeing hope. We're seeing utilization below 60% there. And we're seeing that the number is trending close to to 500 now, bringing it down. And now we're seeing new life in the clinic numbers, conferring care faster. I'm going to add a 9th clinic. We're pouring all these resources into the clinics in order to keep up with demand, but we're making progress. The utilization is dropping. The number of cases has remained around 500, but is a far cry from the 1,000 or so that it was earlier. And once again, faster delivery confers some value here in terms of case counts, and we're right around 500 now. I'm going to add a 10th clinic. And now the game changes. We're at a tipping point, and the affections died out, and the utilization drops like a rocket. Like a rock, not a rocket. The clinics, if we go see them, those 10 clinics are basically empty now. No one's coming in. No one needs care. No care to confer. They have borne the brunt of the public health disaster, and they have cleared that population. But to make this point clearer, I'd like to take this model, this very same model, nay, this very same scenario, and I'd like to run it. And what I'm going to do is press run, but from the get-go, I'm going to go up here quickly and add another clinic. One more clinic, folks. One more clinic. And we're going to speed up the model here. So I have 2 clinics. Not 10, as I did at that peak, but 2. 2 serving this modest number of cases. And you can see the cases kind of knock around. And then they die out. And they die out entirely. Or to do it even more simply, I could have added a 2nd clinic from the get-go. But if we ran that again with 2 clinics, we'd see something kind of similar here. There we go. I'm going to add a 2nd clinic, and then I'm going to run it out. And this one may take off and require a 3rd, but here it is. It dies out. So lesson learned, folks. The model exhibits path dependence. You start with too few clinics, it takes off, and it gets locked in at very, very high levels. It takes, in this case, required here 10 clinics for us to easily bring it down to, in my experience, sometimes you might be able to get it down at 7 or 8. Very large number of clinics. Just 2 clinics, vastly smaller number, you can head it off in the first place. We saw tipping points, we saw path dependence, we see lock-ins. Those are the lessons I wanted to highlight to you on this model. Another model, I'm going to call this version 4 here, and we're going to save this for future models, and I also want to save this for future boot camps, and I want to save this and call this capacity utilization. Capacity utilization. Here we go. And this really should be called, I'll distribute this new one, prevalent case count. Okay, enough of this one. But I think you see, having a model which at once characterizes a service workflow together with a public health situation and characterizes the interaction between them bidirectionally. People presenting to the clinic because of public health needs. The fact that the clinic delivers care helps alleviate the burden of public health needs, and the ways in which they are jointly entrapped in a cycle is of great significance. We have built, deployed, used for policy insight in in multiple health organizations, Australia, and here in Canada throughout the pandemic, in the Yukon, in our province, models like this. But there's many models now that have been done like this, and it's one of the most common: service delivery with public health. So they can answer joint questions about service type, service quality, and its interaction with public health, the impacts of weights on public health, etc. Another one is a situation that's very different. We have an at-risk population that's characterized at an individual level, either with an ABM or with an aggregate, excuse me, or a discrete event simulation, or commonly both. And then we have a broader aggregate population that is characterized with stock and flow. The basic idea is as such. We have a stock and flow model up here that's aggregate. Because it's aggregate, it carries economy of representation. It's very, very quick to run. We represent the large fraction of the population with this. Maybe it's 80%, maybe it's 90%, maybe it's 50%, but a large fraction does not need to be represented at an individual level. Once they reach a certain point in the risk continuum, maybe it's when they're contact traced, maybe it's when they have developed a certain condition, perhaps prediabetes, for example. Maybe it's when they develop metabolic syndrome prior to prediabetes. They become an individuated agent. And we simulated them at an individual level. There are times where in some models we've been involved with, they actually go back to an aggregate state once their needs have been sufficiently dealt with. So this has been deployed, yes, in a real world policy context, in the context of province-wide decision-making for capacity utilization, with UN-10 being used, being the model behind it. And you can find this model described in her PhD thesis as a dissertation that shaped policy that affected everyone in our fair province. So we have an aggregate model built in haste. I might note you can criticize its presentation, but if you're working till past midnight every night, you'll understand. And for breakneck demands as far as getting policy insight to make decisions, you can understand why the aesthetics may sometimes suffer. We have an agent population evolving in terms of infection status, etc., because they've been individuated by reaching a point of infection. And then we have service delivery for them across multiple service delivery workflows. This is, I think of it as kind of a lateral system dynamics to agent-based workflow. You characterize stocks and flows upstream. You don't have to represent every person. A person's just a number right? I mean, they're just counts the number of people who are in this general population, or at-risk population. It's really here that a lot of the action takes place in turning them into an agent with certain characteristics. By stratifying this up, say, we can give them some general characteristics, say by sex or age or what have you, age category, and then we turn them into an agent whose actual detailed characteristics, like their continuous age or their immigration status or what have you, reflects the appropriate stratification over there. We get enormous economies here. Let's open up the budding hybrid SD ABM, and we can see it firsthand. Okay. I would love it if AnyLogic provided better support for this. This one, again, it's called budding, so B. Here we go. And open it up and download it. And I've made the key points with it, but okay, why didn't that? Sorry. Okay. I've made the key points of it. This is to point you to an implementation. the implication, what it lacks in elegance, it makes up for in utility. We have, and it just illustrates the general features of this. Here we have non-diabetic population. Once they are diagnosed with diabetes, according to this flow, they go down to this stock. This event, you're familiar with events, and this event is triggered not by a hazard rate, not by a fixed timeout, not just merely once. It's based on a condition. And one type of transition I didn't show you in this boot camp was one based on transition. And here, thanks, Jeff. Here we basically go through the set of agents in the stock here. We create them as an agent. You may remember this add population. And then we debit them from this. So we remove them from the set of agents to be created. Having done so, having created these agents, the count to be created as dictated by the stock, we and have been taking them out of there. We restart this this event to fire off again the next time the transition reaches over one. So once there's at least one agent to be created, we will create it as an agent according to the population. You may remember this add underbar. We used it to create open populations of agents. There we go. And those agents that were popping in here were created from that upstream stock. Okay, so that was the second major type of modeling. Let's take the third modeling type of evolution. System dynamics-driven agent evolution. So here I'd like you to load in one called CTL state variable. So this is cytotoxic T lymphocyte state variable. And that too is in your list of hybrid models. Here we go. Open it up. And you can select this and download it. And there's a Shutterstock image that if you want to see, you could download it. It's optional. It was added at one point by Jeff McDonald and adds a nice sort of little twist, but it's fine. It will load fine without it. Okay, so here, folks, we have a model. We have persons. The persons are either living or in a dead state, a rather austere view of life. And you'll notice that they die if their viral load goes above a certain threshold. Now, to what does this refer? Well, it refers to a stock in this theory-based model informed by, I think it's a book by Waters on viral dynamics. For characteristic viral dynamics, where we have viruses, free virions here. We have uninfected cells, infected cells, say in the epithelium. And this viral load can infect cells, which then transition from this uninfected state to this infected state. And the immune response, there's an immune response which is stimulated by the presence of infected cells, which builds up immune memory. That immune memory can kill off cells by lysis, killing off infected cells. So, in short, there's a process by which free virions lead to infection that stimulates immune system to cut short that infection. But in the meantime, these infected cells, undergo lysis in a way that releases more free virions. So here we go. The cytotoxic T lymphocytes are fighting these cells, but in the meantime, these cells are releasing viral load, viremia, free virions. Okay. And this leads to a dynamics associated with infection spread within the body, which is quite notable. One thing I haven't addressed, and is a key point of this, in its link to the agent-based, this by itself would be an in-host model, a model of evolution of a host's immune system status and infection status over time. What's different here is that we can get free virions from neighbors. And these neighbors, if we press control and press click on that, are garnered from network neighbors. So each of our network neighbors within our agent-based network contributes some viral load. So the viral load associated with that person, and that allows us to figure out how much viral load, to what viral load we are exposed. So I receive from others a certain coefficient omega times the total viral load from neighbors in my, say, sexual transmission network or in my needle sharing network. So I'd like to run this model with a high viral load threshold. That's the first of these. I'm conscious of the time. We have to move fast and live light on the land. So I'm running that first high viral load threshold, and I'm going to speed it up here. And you'll notice that we see an animation, and the redness of the cell indicates the level of viral load in a person. The width of the cell, or the radius of the circle, indicates the level of immune memory that is felt here. And you'll notice that at first an individual develops very high viral load. It becomes red. And then the width of the radius of their circle expands, indicating their immune system is developing protection against it. And in the fullness of time, once it develops enough protection, enough memory, enough wherewithal to beat out these infected cells, they will suppress that infection, and it will shrink down while they retain immune memory. The infection is traveling around this network, person to person, and as a transmission of person to person, it is leading each successive person to receive an amount from the neighbors, which stirs up secondary responses. But their immune memory helps make those subsequent iterations less serious. Okay, so you'll notice now it's settled into a sort of equilibrium of sorts. Equilibrium in terms of viral load, hence the slight red. Equilibrium in terms of the level of the level of immune activation. And you can see this here, sort of the mean immune response across the population and the mean viral load across the population, as well as the accumulated over time population-wide viral load. We're going to stop this scenario, and we're going to open up, with attention to time here, a medium viral load threshold. The final is it the final? Yes, the final scenario here. I'd like you to run this. Now here, individuals are conferred a risk of dying. If their viral load goes too high, they will pass away. And what's notable, and something I didn't emphasize, was heterogeneity in their ability to control the infection. Heterogeneity in the degree, how quickly the infection can spread, or their coupling to others. So here we have individuals in this network who are subject to infection. And what's notable is some of those individuals pass away. And by passing away, they break the network. The individuals who are particularly subject to being passing away are those with many neighbors, or those with weakened immune systems, or with a pathogen variant which boosts their the growth of the pathogen within them. So here we see this interplay. We see an interplay between a theory-based model articulated with stocks and flows predominantly at an individual level, with the exception of a death model, which can lead a person to be deleted from the population, that does so when they reach a certain viral load threshold. That's a discrete component. And that interacts with a network-based interface characteristic of agent-based modeling by which people interact over the network, by which people are subjected to risk imposed by others, and the dysregulation of some individuals. While it can confer risk to others, if they pass away, the risk conferred by them in terms of needle sharing or sexual contact that would transmit infection, for example, is lessened by virtue of the fact they're no longer contributing to the viral load of their neighbors. Okay, so this was a theory-based model. I'm going to stop this model in the interest of time here. Time is running down. I would just note that, we have often, for some conditions, particularly physiological conditions, certain biological evolution, but also sometimes some aspects of perception or belief or what have you. There's been some elegant system dynamics models, stock and flow models characterized. Often we have theory characterized with ordinary differential equations. And we can capture that within an agent. And in general, we can have, as we've seen here, coexistence within the same agent of a discrete characterization, state charts, and a continuous characterization here with stocks and flows. And we can have impacts of characteristics of individuals onto the broader of in-host issues, onto the broader epidemiology, and impacts of that epidemiology onto the person. When David Vickers and I first published on this in 2007, we conferred the title immunoepi models, and that seems to have stuck in the field. I hear that term from others to this day. Well, this particular example concentrated on communicable disease, you may well recognize that we could use it just as well to look at things like coevolution of weight and weight norms, or coevolution of people's level of substance dependence with and perhaps yes, a level of physical dependency on certain substantive as it interacts with their co-use patterns with others in the population. This can be used in a geographic context or a spatial context. I would particularly note there's a nice model. This may really interest some of you, so I'll highlight it within our, within our hybrid models area. It is called here, the gridded system dynamics has some relevance, but it's not the only one. It is called environmental contamination hybrid, which takes this and applies it in the context of a neighborhood mobility model, where people are exposed to different levels of contamination in an environment. And we see, and I guess I didn't download that, excuse me. But this environmental contamination hybrid leads to people to circulate to different environments. They're exposed to levels of pathogen in that environment. By getting infected with that, they then can get carry that infection to other places and shed virus there in ways that builds up pathogen there. The pathogen decays over time according to certain rates, but it builds up according to shedding. And this can lead to contamination at different locations, and therefore there's higher level induced dynamics associated with these locations that interacts with individual base dynamics. It's a powerful combination and one that can be very, very insightful at a level that a purely accurate model would not be, or an individual level without a continuous representation of dynamics would also have limitations. Yes, there's a hand up. Yes, Sarah.
Hi, thank you. I was just wondering, this type of model that has an environmental component, how is the environment kind of represented in the like state chart?
Um,
Is it different
mhm.
states, or
um,
is not?
yeah, I'll show it to you. I think the easiest thing to do is to uh um talk less and show more here. So because there's been interest expressed here, I will open this up. So this is a pretty familiar type of setup, given that you built a neighborhood mobility model. So we have people in some sort of natural history of infection, state charts, susceptible, shedding, recovered. Um, and then they have a mobility state chart. You may remember this from our model that we built up, where they go between basically home and work. Um, and there's this, going to work where so I should emphasize here, within Maine, there's a set of there's a population, a set of homes, a set of workplaces, right? And they circulate to the workplaces over time. Um, they each are associated with, in the way to which you become accustomed, to a random home and a random workplace, to which they're assigned. Thank you very much. Um, and then at the level of that person, they circulate between their workplace, going to their workplace, it's a parameter, right? Their home, that's the other parameter to which they've been assigned, right? And they can pick up infection in one of two ways. Remember your question from a few days ago. One pathway to pick up infection is via environmental contamination, according to a hazard rate given by the current exposure level, the location in which they're located, times some chance, some coefficient, reflecting how to translate that into a hazard rate. This, by contrast, is the possibility that they could be infected by, I think this is initially infected, actually. They can be initially infected. And then they can shed and they can recover. We could add some person-to-person transmission with a transition here, as you've seen before. But you'll notice that the workplaces here and the homes like them have a pathogen reservoir, and this is a stock and flow model, right? This builds up pathogen according to some per capita shedding rate times the count of infective agents that are in range. And then the pathogen reservoir decays at a certain lifetime of pathogen. So here we have a dynamics at a workplace of a reservoir and a dynamics indeed at home that's similar. And by visiting the workplace, it knows that when they're at the workplace, they're exposed to a certain level of pathogen, that's current exposure level, right click, right, and then click on it. And this is in that same agent. And the current exposure level is, if they're at work right now, then their exposure level is what it is in the workplace. Otherwise, it's according to the pathogen reservoir for their particular home, because each workplace including the one to which they have a link, have a reference, and each home has a pathogen reservoir according to it. So I don't know if
Yeah,
that answers your
it does.
question.
Yeah, it's kind of based at the location. That's what I was asking. Yeah, perfect.
Yeah, yeah. It's the location they go to during the day, or you could do it the location at which they are currently located. You could that would take a slight amount of finesse so that you treat sort of um it wouldn't be bad. You'd probably yeah. You would want to know like okay, what's the notion of abstract location? And a home would qualify, a workplace would qualify. But in any case, this is very easy a way to do it, and we can have them evolve in terms of their risk according to that. And then in each of these locations, there's some sense of who's there. Count the number of infected people at the location, which again is given by a formula here. For the it's in Maine, formula in Maine here. Forget the number of people at the location. And basically it asks, okay, for that location, how many agents are in excuse me, this is get all people at location. This is count effective at location. So here, right. So I think right, where's the pardon me for just a second. Right. So no, wrong model. Sorry. This one here. Yeah. This is that model. Here's the workplace, right? And here's this shed pathogen. And we are asking about main.count infected in group. Okay. And main count infected in group is over here. Come on. Count infected in group. Yep. And here this function gives a certain group of people, and it asks how many people in that group are infective. And the thing passed to it as the group here is the agents who lie within a certain range of them right now, within a range of 10. So anyway, that gives some guidance about how that works. I hope that's helpful. Okay. I'm not quite done with these, and I do want to get to the issue of platform choice and so on, and I am fading very quickly here, I'm afraid. Okay. So let's go back to slideshow. Right. And there's a set of other ones provided that illustrate this. Another one is agents drive aggregate system dynamics. So here we have like an agent population, say of companies, we have an aggregate system dynamics stock and flow model, and we have an agent population, say tobacco companies, who pose a certain footprint on advertising and promotion of tobacco use or vaping or what have you, and sugar sweetened beverage consumption, and that can lead to flows of individuals within this population, say from a never smoker state to a current smoker state or something like that. And there's the basic health economics model, which we've already looked at, which basically confers something like this. We have a high level one that accumulates high level stock and flow, which accumulates life years lived, or accumulates qualities, or accumulates undiscounted costs or discounted costs. And then we have a set of individuals who contribute to that accumulation over time. Finally, there's a model where we have an aggregate system dynamics model, which drives an agent population. And I don't think I'll show this to you right now, but we have models, for example, where there are environmental dynamics associated with, say, mosquitoes. Um, uh, Within Saskatchewan, and I would say Canada more broadly, it would be a um, core value proposition to build an agent-based model that attempts to characterize the full extent of the mosquito population. There are agent-based models of mosquito dynamics, and actually they're very insightful for things like egg laying and location of how certain types of climactic uh, or weather conditions, meteorological conditions might affect egg laying. Um, and can be used to characterize interventions in as much as they seek blood meals with individuals who might be um, susceptible to malaria or might have malaria now from which the mosquito could pick it up. So the use of bed nets and the use of fogging or what have you is something that can be examined. Um, Here, we're characterizing mosquitoes in stock and flow models. And those stock and flow models depict mosquito numbers. And we have an agent population of people. And those people have risk imposed on them by the mosquito population that can affect their health status. So their health status is characterized by state charts. Incredibly important for things like West Nile virus is their level of comorbid conditions, their age, and general immunocompetence, et cetera. And we can capture that very richly for an agent population. And in fact, this coupled with the budding model talked about earlier, we could have most of the population at low risk characterized with stocks and flows itself, but individuals who have a certain number of comorbid conditions or certain immunocompromising situations like the presence of a kidney that needs immunosuppressant drugs, et cetera, or perhaps advanced stage renal disease, or they're turned into an agent, and the evolution of that agent is impacted by the mosquito population. Um, so this has some relevance. You can argue that to a degree, something similar is going on with that pathogen reservoir. Although those pathogen reservoirs that they live within other agents. If you had something like a pathogen reservoir in the whole environment, something like maybe for particulate matter or level of adverse body image advertising or what have you, and that infected agents, it would fit into this characterization. Okay. I think I'll stop there for my characteristics of hybrid modeling. I cannot emphasize enough that hybrid modeling helps add to the nimbleness of modeling, helps you learn more, helps you adapt to your learning more effectively, helps use the right tool for the job for different areas of model, helps you change your modeling strategy over time as your insights grow about what things need more detail, what things need different types of detail, and really provides a best of both worlds type of approach. As a key leading practitioner of hybrid modeling in a health context worldwide, I cannot speak enough about the value that this is delivered for health insight, for substantive credibility of models, for ability to tease out certain types of factors, and critically, for ability to capture certain risk factors and the effects of certain interventions, which require a certain requisite level of detail. Also for ability to inquire and learn from the models about certain factors as they affect things. This is not an approach which appeals to purists on any one tradition, and you'll find some partisans out there who belittle it. But from the authenticity of tremendous lived experience, I could say we have found it worthy. We have found it incredibly powerful in our arsenal of models, to the point where most at-scale models we build these days are hybrid models. Hybrid models in one of those 5 compelling patterns. that we have just traversed. So those are all my comments on hybrid modeling. I hope those build up some points of reference of areas of particular value delivery when it comes to the mixing and matching of these types of modeling that we have covered in this boot camp. Agent-based modeling, system dynamics modeling with a particular attention here to the simulation tradition of stock and flow modeling, and finally, discrete event simulation for capacitated resource limited workflow progression and service delivery in defined workflows. Okay, those are all my comments. I'm glad to answer questions about